equals x to the 3/2 in the first quadrant in such a way that its distance from the origin increases at the constant rate of 11 units per second. So so let's sketch out what that looks like first here, as we would do it in any related rate situation anyway. Then we're given that rate of change, the change in the distance, and then also, so we're trying to find is dx dt when x equals 3. So if we sketch this out, only looking at the first quadrant, I don't actually care what x to the 3/2 looks like. It doesn't matter. What matters is that the distance from the origin to some point on that curve, whatever it is, that distance is going to be, it's going to have two components. It's going to have the horizontal component x, it'll have the vertical component y, and this distance, let's call, I don't want to use d for distance because we use d. That's what the book did. I guess I'll just use capital D. Okay, so that's our distance. All right. So once we've got a sketch or a model, a sketch of what's going on, we can generate our model, a mathematical model, by trying to think like, how do we relate all three of these variables together? This is a right triangle, so we can use the Pythagorean theorem. Turns out, if you didn't know, the distance formula is the Pythagorean theorem just for coordinates. Anyway, that's not really important. So our model then, so this would be step 2, I guess. Our model is going to be x squared plus y squared is equal to d squared. Okay, we're only given information about x. So there's a number of ways that we can do this. The book takes and solves for d on its own first. I don't hate that method. It's fine. I think you can also get at it by just taking, I just want to look at my work from the other day when I helped a student with this. I think you can also get at it just by taking it in this form, taking the derivative in this form. Yeah, you certainly can. And that's probably what you're going to likely do, because that's how we've done it. Most of these Pythagorean theorem problems, we haven't kind of isolated the variable and then taken the derivative. So what we'll do here, since x, y, and d are changing with respect to t, we're going to get 2x dx dt. This is step 3, I guess. We're going to get 2y dy dt. Actually, no. Yeah, we can actually, I'm going to simplify this a little bit. Sorry, I don't have to do what they did, but we have x, y, and d here. We don't have any information about y. One way that we could approach this is we can take the derivative, as I was about to do, and then figure out what y is. That's fine because we have a relationship between y and x. The only problem, the big problem that's going to show up, is we don't know anything about dy dt. So that's exactly what I was about to run into when I realized it. So what we want to do actually is eliminate y first, then take the derivative. So I almost kind of ran into a trap there. I apologize. So we'll have x squared plus, and then I'm going to take y is equal to x to the 3/2. So I'm going to plug it in right here, and we'll simplify this model. So it'll be x squared plus x to the 3/2 squared is equal to d squared. Simplifying this, we have x squared plus x cubed is equal to d squared. Okay, and there's not really anything that we can do there. Those are not like terms. Now we can go to step 3, which is take the derivative. So we've got 2x dx dt plus 3x squared dx dt equals 2d times d dt. So 4, write down everything that we know. So we want to figure this out when x is equal to 3. Yes, when x is equal to 3. We want to know dx dt, so that's unknown, and that's fine. We know d dt is equal to 11. All right, and then figuring out what d is, we can do that in a couple of ways. Probably the easiest way is we have an equation for d squared right here. So if we do some scratch work off to the side, we know that when we plug in 3, d squared will be equal to 3 squared plus 3 cubed. And so then we can work out what d is. D squared will be equal to, this is 9 plus 27, that's 36. D then has to be equal to 6 when we take the square root. We're not worried about the -6 because d is a distance, so we can ignore the negative component of taking the root there. So d is 6. Plug everything in and solve. I'm going to skip that step. I'm going to go right to step 6 again just to sort of save some time. You end up with dx dt is equal to 4 units per second. All right, questions on number 60? Okay, let's go on to number 50. It's going to be helpful for you probably to open your book and look at this if you really want to follow along here. This is the situation. We're designing a box with a lid. A piece of cardboard measures 10 by 15. 2 equal squares are removed from the corners. 10-inch size shown in the figure. 2 equal rectangles are removed from the corners so that the tabs can be folded to form a rectangular box with a lid. So this is the situation that I'm going to be working from. I want to first write a formula for the volume. And I suspect that that's where most of the hang up is, but we will, but if it's the other parts, then certainly let me know. So the formula for the volume will be length times width times height. Okay, so if you imagine taking this cardboard and folding it up here on the sides and then folding the lid over top, what you'll have is the height of this thing is going to be x. So just write that down. Okay, then let's think about what the width of the base would be. So again, when this is folded up, we'll have the width of the base will be the other component. Let's be the width of the box, I guess. So what would that be? Well, it's just this dotted line piece here, right? And so so you think like, well, what is that? Well, we've got 15 is the whole thing. We're going to want to subtract off x and subtract off x, but that'll double count the lid, right? So it'd be 15 minus 2x. I mean, if that double counts the lid, then what do we have to do to get just the dotted line? Am I looking at the wrong problem here?
No, but I think you're supposed to use 10, not 15 for that part.
For this piece, I would use 10, right?
Yeah.
I thought 50, like, it was asking us to, like, switch those numbers. Because, like, if you just solve it how it is, like, then you're just solving 18.
That's right. You're solving the original. Yes. You're right. Okay. I'm sorry. Yeah, it says to switch around the 10 and the 15. Is that right? Yeah, but this time remove the 2 equal squares from the corners of a 15-inch side. Yeah, okay. So you're right. I'm sorry. So we'll end up being 15 minus 2x because we're removing the corners from the other side. So you'll end up with 15 minus 2x. And then it will be 10 minus 2x. But what I was saying on the 15 side, which is no longer 15, is that you're going to have to cut that in half because otherwise you're double counting it. So yes, you end up with this. Thanks for pointing that out. So we got x, 15 minus 2x. And then 10 divided by 2 is 5. 2 divided by 2 is 1. So you get 5 minus x. Okay, there we go. So there's the model for volume. Questions on that? Okay, so at this point, you're just going to graph the the model for volume, find the maximum. The domain will be from 0 on the X to wherever that, well, it's got to be less than 5, right? Otherwise, you're going to end up with a negative volume. So the domain, I think, is from 0 to 5. And then you can just go from there. Then the analytical method would be finding the derivative and the critical points.